Our next speaker is the Philip S. Weld Professor in the Departments of Chemistry and Chemical Biology, Earth and Planetary Sciences, and the School of Engineering and Applied Sciences. He was also selected to the National Academy of Sciences, American Philosophical Society, and the American Academy of Arts and Sciences, just to name 3 of the 17.2 million science groups that Professor James Anderson is a part of. I don't know how he can keep all those groups in his mind. At some point, when he's checking the mail, it's just got to be like car payment, water bill. Oh, I'm a fellow of the American Association for the Advancement of Science, or something along those lines. Please give it up for Professor James Anderson.
If you so right as forward. Thank you. Well, thank you for coming tonight, and thank you for Sustainability for the invitation. I'm going to look at 3 aspects, and it, as we will see, involves many subjects, including economics. But before us are 3 issues: climate instability, a formulation of climate change, as I'll describe in a moment, why does it matter, and who's in control? Who's in control now, and who will be in control the year after you finish at this university? So, formulating the problem, climate instability. Another way of formulating it is to call climate change global warming. And as I've said many times in the classes that I teach, I only utter that once because I never speak of it again for 3 fundamentally important reasons. One is that the oceans occupy 70% of the land, of the area of the Earth. The oceans are 4,000 meters deep. They have massive heat capacity, and heat flows into the system, but the temperature changes very little. Another reason is that the ice caps, the Arctic, the Antarctic, and the third pole, which is the Tibetan glacial system, the temperature there doesn't rise past the freezing point until all of the ice has disappeared. So all of these factors constrain any change in global average temperature, which is quite often cited. But the other more crucial and somewhat implicit problem with the term is that it carries no imperative with it. We don't care if the globe warms. People move from New England and northern Midwest into the South. It has no political imperative, and it carries with it the connotation of slow change that's reversible. And it's the reversibility in that term that is the serious aspect when we're embracing what's actually going on in the climate structure. Climate instability, however, carries with it a very different message. So we formulate this in terms of climate instability because instability in physical, chemical, and biological systems implies that the system can occupy one particular state and then move to another state if it's forced to do so. But when it moves to that other state, it does so irreversibly. And this is a typical characteristic of all physical, chemical, and biological systems. So if we go from a condition of ice in the Arctic and Antarctic, with some in the Tibetan highlands, and we move to a condition where the ice is gone, we cannot get back to that original state. And the reason we can't get back are the intrinsic feedbacks in the system that control that irreversibility. And in fact, this is an exquisite system. It's cold at the polar regions and it's hot in the tropics. It's a balance that's extremely important for the larger dynamical aspects of the atmosphere itself. So let's see how this works. Dan Schrag has already mentioned this, but the key axiom here is that the time scale for irreversible change that triggers this instability is set by those feedbacks. And the central feedback from which virtually all others cascade is this issue of the loss of Arctic ice. So here we are in 1980. I actually pulled this up this morning from the Cryosphere Today site, It was about 8 o'clock when I pulled it up, and I went back on the site a couple of hours later, and it had crashed because this is the week of minimum ice coverage, and so many people went into that site that it crashed the system. But fortunately, I managed to garner this at 8 o'clock this morning. So here, this is the 15th of September 1980. This is a couple of days ago, and as Dan pointed out, not only is the Northwest Passage open, we have a clear pathway that triggers the feedbacks that are most important on this system. As the ice comes back, warm water comes in from low latitudes, bringing heat into the Arctic basin. This is the problem with. There, is that all right? So, atmospheric motion into this system as the ice and snow disappears also brings heat into the system, accelerating the rate of melting of the remaining ice. But also important is the fact that the ocean is black. These color codes are simply to represent the fractional amount of ice, and this is really, of course, white, as is Greenland, as shown here. And all of that heat, rather than being reflected back to space, is absorbed into the surface waters of the ocean. And these ice systems are only 1.5 meters thick now. If we go back to 1955, this was locked in all around the extremity of the Arctic, but it was 3.5 meters thick. We have exquisite data from nuclear submarines that were traversing the area. So these feedbacks then control the rate of disappearance, and we've lost half of the Arctic ice. The second half will disappear far more quickly than the first half. And it's that acceleration resulting from the feedbacks that also tells us we can never get back to this system because there's no mechanism to actually extract heat and rebuild that ice system. So why do we care about that? Well, this depends on who you ask. And if you ask Shell Oil, they are a bit miffed because they're running a little late to try to extract oil from the bottom of the Arctic Ocean that's opened up with the disappearance of that ice. So 1/3 of all global reserves of fossil fuels lie under the Arctic Ocean. So as that ice pulls back, one of the responses is to go after the rest of that petroleum. But of course, it's the forcing of the climate from the release of carbon dioxide that created the removal of ice from the Arctic Ocean in the first place. So there's a profound irony. The other side revolves around this point that Dan Schrag pointed out. 1985, there was no melting on the surface of Greenland. And Greenland is 3,000 meters thick down the spine of the system. 1992, meltwater began to appear on the surface. These are our satellite microwave data, very accurate. 2002, it began to spread. 2005, nearly half the area had meltwater on it. This last summer, the entirety of the Greenland glacial structure was covered with melting water. Now, this water doesn't run off as water runs off a duck's back. It actually goes down into the fissures that exist in the structure of that glacial system itself. That water pours all the way down to the base, and it breaks the bond between the ice structure and the bedrock, and that bond that retains the outward motion of the ice structure of Greenland is what develops its stability. In fact, the Greenland glacial structure looks a great deal like a medieval cathedral. It's very high all the way out to the edge, and then it drops precipitously at the edge. The flying buttresses are the only thing that retain the physical stability of that system. And once that water penetrates into the union of the ice and the bedrock, the system will slide sideways and collapse from the center. It won't melt. So what happens? It contains 7 meters of sea level rise. So let's just look locally. This is Cambridge. The Harvard property is shown in yellow. This is the Back Bay. And so let's just take 1/7 of Greenland and add that in. That's 1 meter of sea level rise. You can see the athletic fields next to the football field are now underwater. Now, of course, Harvard is about to drop $10 billion on a campus in Alston. Let's add a couple more meters. That's 3 meters. Now, the only attractive feature of this is that MIT goes under before Harvard. Not only that, it brings a whole new connotation to the word river house. So those of you in the Radcliffe Quad are protected for the next few years. The river houses will move on. Okay, now, what's the response? This is from the New York Times last week. Headline on the front page, New York is lagging as seas and risk rise, critics warn. So Mayor Michael Bloomberg is investing a huge amount of money to analyze what's happening, because this is Manhattan. 3 meters of sea level rise takes out the southern third of Manhattan. Of course, Manhattan depends rather sensitively on its underground electrical and subway systems. And if you try to dike and those dikes are breached by either rising sea level or storm surge, salt water pours into those systems. Now, it's my contention that it's the mayor, the leadership of the cities of the world that are going to be a huge part of the solution. So are CEOs. As we heard in the last talk, CEOs care a great deal about the stability of structure. And of course, Michael Bloomberg is both. He's very active. But New York is beginning to brace itself for this, because the predicted rise by the end of the century is somewhere between 2 and 3 meters of sea level rise, with a tail running out to 6 to 7 meters of sea level rise. So this brings us back to the last question: who's in control? We looked at climate intrinsic instability. We now know why it matters, and there are many other reasons. So let's look at who's in control. This comes back to the fact that the global energy enterprise is an $8 trillion a year business. It dwarfs any other competition. In fact, a 1% niche, which I'm sure any of you are capable of executing, is a mere $80 billion. So as soon as you graduate, you want to put in a 1% niche in this international affair, because none other has the leverage that this does. But this is a descriptor from the New York Times of just a year ago that analyzed the new energy picture. It analyzed oil sands coming out of Canada that have now demonstrably placed Canada in close competition with Saudi Arabia for oil reserves. The drilling in the Arctic, I've already mentioned. I showed Shell's operation. But these deep water systems in the Gulf, off Venezuela, off of Africa, completely recast the numbers here. Canada, of course, is third in this analysis in oil. The United States was 13th. It was fifth in natural gas, 272 trillion cubic feet. But in the last 12 months, this has gone from less than 300 trillion cubic feet to 3,000. This is twice the reserves of Russia, which was the king prior to this. So who controls this? Well, this is on the front page, again, late last week in the New York Times. Fossil fuel industry ads dominate TV campaign. So we know who controls it. But this is the crucial final point I want to make, and that is who controls it in the future. And the fundamental axiom here is that the universities have a central responsibility to prepare graduates for the future. That is, when you walk out with your diploma, are you armed with what you need to know to deal with this problem and proactively engage in it? But do universities fulfill this responsibility? Well, first of all, when you walk out, the issues that face you are the technical forces shaping the modern world. That is driving the very rapid change. Yes, I agree. Second thing is, where are the frontiers of innovation? What are the implications for any professional endeavor? Because we used to think, well, you study science and technology when you go into science and technology, but that's a fundamentally incorrect assumption. as important in international economics. We've already seen that emerge in these presentations. If you're going into government, going into ethics, public health, law, and education, these are fundamentally crucial connections. What about public policy? What strategies are founded on reasoned, thoughtful, technologically sound basis? Is the United States public policy based on that? You listen to presidential debates, and it's stunning. Not only is it garbage that's discussed, but the journalists asking the questions don't call the candidates. This is an unacceptable union. So what we have is a structure of economics in the undergraduate curriculum. We have public policy and government. Those are nicely connected. What about physics and chemistry? Physics tries to flunk everybody out of the freshman course. Chemistry does exactly the same thing. These are the only two pursuits that try to drive freshmen away from that intellectual endeavor irreversibly. They never come back. So we graduate people who are fantastically intelligent, but they don't have the information required to enter into hand-to-hand combat over what's coming in the next few years. So when we bring these together, and first of all, we don't separate physics from chemistry. That's a ridiculous concept. Nature never heard of the separation between physics and chemistry. Here we have chemistry departments and physics departments. Students have to take quantum mechanics and thermodynamics from chemistry, and then in a virtually different language from physics. Massive waste of time, drives not only a flunk-out issue, it's a boredom issue. Okay, so physics and chemistry are now joined. They join in this combination that is defined by a liberal education today, which is not taking more in different courses, but it's integrating these together so they're a powerful union, arming graduates across the country, of which there are 2 million a year that now know how to vote. Thank you very much.